Okay, great. So thanks everyone for coming. I see a few new or different faces, so I'll just remind everyone that um, we usually ask the speaker to talk for approximately an hour, but we encourage the students and everyone attending to interrupt with as many questions as they can when things are unclear. So, maybe it takes an hour 15 or an hour 30, but we also will respect the speaker's time. But anyway, let this just be kind of like a formal invitation to ask as many questions as you need to satisfy yourselves. Anyway, so there's been a recent burst of activity by a number of groups working on the SymTFT for continuous symmetries, and this has generated a lot of interest and a lot of questions. And so today our speaker is Federico Bonetti, who has written a very intriguing recent paper on SymTFTs for continuous non-Abelian symmetries. So whenever you're ready, take it away.
Sure, yeah. Thanks a lot for the introduction and for the invitation to give a talk today. And indeed, so I would like mostly to tell you something about my paper in collaboration with Michele and Ruben, but we will see that I will also touch upon elements that have been covered in also these other very nice papers that have appeared recently and that sort of discuss quite similar related topics. So yes, let's test the slides. Good. So maybe, well, presumably this audience, of course, it's extremely familiar already with the concept of generalized global symmetries and why we sort of care about them. But I thought to give a little general motivation and introduction, this could be a good starting point. Essentially, what we have realized in sort of recent years that there is very powerful generalization of the textbook notion of symmetries of quantum systems that is really encoded at the end of the day in this realization that we should really think of generalized global symmetries of a system in d dimension, say space-time dimensions, essentially as being the same as the topological operators that we have in the system that we would like to study. And here, for the rest of the talk, I will have in mind a continuum, a QFT in the continuum formulation, but I would like maybe to state here that many more things are possible and very interesting to study on the lattice, for instance, and similar considerations apply. And why do we care about generalizing the notion of symmetry? Well, essentially because we know that the ordinary notion of symmetry gives us a lot of power, especially in situations where it would maybe be hard to study the quantum field theory of interest by other means. We know, for instance, that if we have global symmetries, we can organize the spectrum of operators that we have in our model. The symmetries, of course, could have anomalies, and we know that matching them following Toft gives us very powerful constraints on possible RG flows, for instance. But we also know that we can break ordinary symmetries. Sometimes there is a Golson theorem that holds, and related to the idea of spontaneous breaking, we also know that there is this paradigm or this hope that we can characterize phases, IR phases of quantum systems in terms of symmetries. And while we know that the ordinary notion of symmetry is not powerful enough to realize this paradigm fully, there is mounting evidence that if we allow the notion of symmetry to be generalized, then we can also extend Landau's paradigm in a very interesting way. So these are just a few motivations. There are others that sort of demonstrate how I think there is indeed quite an important motivation in trying to know ultimately what is the most general notion of symmetry of a quantum system and trying to identify the dynamical implications of those. This is, of course, a very broad and very general goal, long-term goal. And we have seen really a sort of a great acceleration. If we can imagine starting from our textbook continuous symmetries, they have a Noether charge. network current that gives rise to a conserved charge, and we can exponentiate it to get these topological operators. This is, of course, very well known and understood. It's mostly, I'm fixing my notation in this slides and sort of giving a very brief reminder. And essentially, we can layer up by relaxing some of the assumptions that we have in the ordinary case and finding richer and richer structures. In a first level, we can play with dimensions and codimensions, and we are in the world of p-form group symmetries, where crucially though, the fusion of these topological operators implementing the symmetry is still group-like. In a sense, at a higher level of sophistication, we can start mixing in non-trivial ways different p-form symmetries, generating in the process higher groups. And in a sense, the final or like the more complex layer that has been studied recently is the one where we really are in the full realm of non-invertible and categorical symmetries, where essentially now we have topological operators that are no longer labeled by elements of a group and whose fusion is richer. The hallmark is, for instance, the presence of several terms on the right-hand side of the fusion, and the fusion coefficients themselves can, in general, be partition functions of TQFTs. This is an extremely rich and interesting story that has, in a sense, a very long history in lower dimensions, say 2 and 3, and a much more recent but equally rich story in dimensions 4, 5, 6, for instance. And there have been clearly a lot of work, and probably I could quite literally cover a whole slide in citations. So I decided instead to give here a few nice reviews that have recently been compiled, and they're really a great way to sort of make inroads into the topic. And all of this is sort of to testify the richness of this sort of program. And the other main ingredient that relates to the title is, of course, the SymTFT picture, or sometimes I will refer to it as the sandwich construction. It is basically, let me remind you, this idea that we can actually study many non-trivial aspects of symmetries of a system that lives in these space-time dimensions using an auxiliary theory that lives in one dimension higher. And this has also quite a long, like the idea itself has a long history and has resurfaced more recently in the context of generalized global symmetries, and it has proven very powerful. It's really a very nice way to think about symmetries in various contexts. And most crucially, it captures not only group-like symmetries, but also symmetries of more categorical or non-invertible flavor. And so given that this really seems to be a very powerful language we have at our disposal that has already been successful in describing very sophisticated finite symmetries, a natural question in a sense remains. Can we revisit the textbook, say, Noether continuous symmetries through the lens of this language of the symmetry TFT? And in my mind, there are several reasons why it would be quite interesting to complete the picture in this sense. On the one hand, just to have a, say, unified framework where we can really then discuss or make progress towards this ambitious goal of trying to characterize what is the most general notion of symmetry that a quantum system could potentially ever have. And clearly, if we don't control continuous symmetries, we are missing an important piece of the puzzle. And in a sense, maybe even more interestingly, we know that even this sort of group-like continuous textbook symmetries can have interactions, so to say, with more modern ingredients. They can participate, for instance, in higher groups, mixing with other p-form symmetries of higher degree p higher than 0. And we also know that there exist examples of symmetries that are not group-like, but that can be regarded as being continuous. or non-finite in any event. So in other words, with this, I think this is still a key question, and there has been progress, but I don't think it's completely settled yet. And it will be really nice, I believe, to really have control over this aspect of the story to really improve our understanding of the broader picture. So given essentially this sort of motivation and overall sort of state of the question that we would like to address, I will then discuss a little more the sandwich construction. This is merely a review, but I thought it would be good to essentially set the notation, the terminology that I will be using, and also I will be highlighting some well-known aspects of, in a sense, one of the simplest examples of the sandwich construction, just a finite abelian group-like symmetry, to sort of emphasize the aspects that are going to look a little different in the continuous non-Abelian world. And after that, I will switch gears and discuss the proposal on how to deal with this non-Abelian continuous symmetries. I will first sort of state the proposal in a purely field theoretical context, but then I would like to highlight how it's actually very natural from the point of view of string theory and holography. We will see that both in the context of geometric engineering as well as in holography, it's something that emerges quite naturally. And finally, before the conclusions, I would like to discuss how we can recover some aspects of the action of continuous non-Abelian symmetries on a quantum system using the sandwich picture. So this sort of like will be a sort of proof of principle of what sort of questions we can start addressing. But I do believe there is much more to be done and even more interesting avenues to explore. Okay, so if there is no question on the sort of introduction, I would like to continue with a brief review of the sandwich construction. So essentially, indeed, what we would like to study is a given quantum field theory in the space-time dimension that enjoys a global symmetry S. And of course, the more familiar case is the one where this is a group, but it could be also be a symmetry category. And what are the main ingredients that we have to construct? Well, the main character is the SymTFT itself, is an auxiliary bulk theory that lives in one dimension higher, topological, in the case of finite symmetries, and together with a gapped topological boundary. I will denote B, and I will also refer to it occasionally as the symmetry boundary. This is really the place, in a sense, where the abstract symmetry S lives, so to say. On the other hand of the sandwich, instead, we have what I will refer to as the physical boundary, denoted T hat. And this ingredient doesn't have to be topological. It can be, if we want to study, if the QFT we want to study is itself topological. And finally, sort of implicit in this whole idea, this is useful to what we want to do in D dimensions because there is an isomorphism between this sandwich construction, so to say, and the result of the squashing of the interval into something D-dimensional, which is which has to be the QFT that we would like to study. And in a nutshell, why do we introduce this extra dimension? It's precisely because we want to separate, even physically in space-time, so to say, the abstract symmetry S from the specific realization on the physical system that we would like to study. So in a sense, this is very analogous to the thing that happens all the time in mathematics, like and in physics as well, where we want to maybe talk about a symmetry group, like want to study the abstract property of a group and of its representations without committing to study a definite physical system that has its specific realization of that symmetry and those representations. So the sandwich really separates in space these two parts of the story. And this applies both to the topological operators that realize the symmetry as well as to the objects that are charged under the symmetry. So let's briefly remind ourselves on these two main sides of the story. As I mentioned in the previous slide, we could say that the symmetry boundary is really the place where the symmetry S lives, so to say. And to be a little bit more precise, I mean that it supports these topological operators that I will call S with some label A. And it's really beneficial to think of them as being on top of the topological boundary. And when we close the sandwich, we are essentially pointing out how the abstract symmetry that we would like to study is actually realized in the system that we actually, in the quantum field theory of interest. So here I'm using the notation D for the defects in the quantum field theory that we want to study, and I'm using a different notation S for the sort of abstract symmetry generators that live on the symmetry boundary. To emphasize this separation that I mentioned earlier, so that the abstract symmetry and what it acts on. But as you can see now, there is literally a separation in space between, in a sense, the dynamical degrees of freedom that would live on sort of yellow surface and the symmetry that is now living on the blue one. So how do they actually talk to each other in interesting ways? And indeed, we see what has emerged is that in order to realize an operator which is actually charged under the symmetry of interest, we have to stretch something, stretch one of the topological operators of the bulk. This picture is this red line between a topological endpoint E on the symmetry boundary and the not necessarily topological endpoint M on the other side. And upon squishing the sandwich, we recover a charged operator. And this is it's quite a general picture, and importantly, it applies definitely beyond group-like symmetries, but and it captures many important aspects of symmetry. Here, I'm just going to mention briefly three of them. The first is that it can be used to capture anomaly, and indeed, there have been very recent, quite recent and very interesting body of work in which the SymTFT technique is really instrumental in a sense, really defining and computing what we mean by anomalies in the case of some, for instance, categorical symmetries. And more generally, this picture is perfectly suited to study things like discrete gaugings and topological manipulations, because ultimately it's sort of a replacement of the symmetry boundary with another boundary while keeping both the bulk as well as the physical boundary untouched. And finally, something related to the previous slide, the picture that has emerged recently is that the symmetry field theory is really important to study the representation theory for symmetries, including categorical symmetries. Ultimately, because as we have seen in the previous slide, and we'll also see later on, both the symmetry operators as well as the charges ultimately originate from topological operators that we see on the so-called quiche. So that's the side of the story that does not depend on the particular physical theory you want to study. It's the bulk together with its symmetry boundary, the gapped topological boundary. And indeed, essentially, we have seen in the previous slide, so this would be like the S topological operator on B, or this red operator and its topological junction E. Essentially, all the representation theoretical data is encoded in these objects, which is good news. It's realizing the proposal, our intent of separating sort of more representation theoretical aspects to the particular system that we would like to discuss. And all these features are already, or many of these features are already present in what is maybe the simplest possible example of a SymTFT. And here I'm just sticking to very simple, a discrete abelian zero-form symmetry. The bulk theory is a very well-known BF theory at level n. And if we want to focus on the zero-form symmetry, which is exactly what I aim to do, I stick to the Dirichlet boundary condition for the A1 gauge field. So these are both gauge fields in the continuum formulations with integral periods in suitable units. And we know that this five-dimensional bulk theory has topological operators, including Wilson lines for A and Wilson surfaces for B, that have a non-trivial linking. And what we also know is that if we commit indeed to the Dirichlet boundary conditions for A, we can take the holonomy of B and project it onto the symmetry boundary, where it's going to realize for us this sort of abstract generator of Zn zero-form symmetry, if you wish. And we can also take instead a Wilson line of A and have it end perpendicularly on the symmetry boundary, thereby giving us charged, like the topological part of what will be a charged operator when we close the sandwich. And as I alluded to earlier, the key point is the interplay, if we wish, between the endpoints that I'm denoting by E0 and these S3 generators. But in this case, it's very easy to find out how these two ingredients interact, because we can literally resort to the bulk linking that we had previously and essentially use that to understand how the symmetry operator acts on the endpoint. And this is, of course, maybe fairly obvious too, but I'm emphasizing it here because in the non-Abelian world, things are going to look a little different. So that's why I'm sort of stressing this point here. Okay, so I think, yes, I think that concludes this brief review. I'm pretty sure it was probably mostly familiar material. And so now let's get to the more interesting part of the story, namely, can we devise a way to mimic this construction in order to capture a continuous symmetry, and in particular, something that can be non-Abelian if it's a zero-form symmetry. And well, so let me state what our proposal was and and essentially our starting point that, as we will see, is quite well motivated from geometric engineering and holography, is that if we want to study a zero-form symmetry G, and let's focus on the non-Abelian case, but we could also discuss Abelian. Ultimately, we simply consider Yang-Mills action in one dimension higher. Now, of course, this is not a topological theory. It's an interacting theory and has no trivial dynamics. So part of our proposal is that we should understand this Yang-Mills theory in a specific limit where the Yang-Mills coupling goes to zero. And how this limit is understood and implemented, it's something I will explain momentarily. What we find is that if we define this limit in the suitable way, we obtain, as a result, a topological theory, which is a non-Abelian generalization of the BF theory, so to say. So here I'm writing schematically the action, and it's sort of manifestly topological. I haven't really explained yet what the various fields are, but I will do so in a moment. This is more like to give a broad picture of what's going on. And as I mentioned, we also expect similar considerations to be applicable in the world of abelian continuous symmetries, in which case we can modify the p-form degree and have it greater than zero. But again, in the crucial idea is that we should consider a suitable zero coupling limit, and we will have the emergence of a BF-like theory. And in that sense, this proposal connects to previous proposals in the literature, especially this last equation, related to how we can think of the SymTFT for a continuous U1 symmetry of some p-form degree in terms of a BF theory that, as we will see in a moment, has sort of one gauge field which gauge group R, so to say, and another usual U1 gauge field. The point I'd like to emphasize in this slide is that these BF theories or BF-like theories at first might look a little exotic. At least that's how they sort of looked to me the very first time I encountered them. And then I sort of convinced myself that actually they can be seen emerging from much more familiar theories, like literally Maxwell theory or Yang-Mills theory in one dimension higher, which is also ultimately how, in my mind, and sort of a natural connection with string theory is also established. But before going there...
Sorry, Federico, can I ask a question?
Yes, absolutely.
Unless the bulk is two-dimensional, even in the zero coupling limit, Yang-Mills will not be a topological theory, will be a gapless theory. So when you claim that this is dual to the non-Abelian BF theory, what do you mean? It cannot be an exact duality, right? It should be that it is some sector of the theory, right?
I completely agree. So I hope that my next slide will clarify this a little more.
Okay.
In case we can revisit the question in a moment. But
okay,
it's an excellent point. It's very important. Thank you. So indeed, what sort of duality do I have in mind? What sort of manipulation? So essentially, it's sort of summarized here. Well, again, so to fix notation, we have our usual, say, potentially non-Abelian field strength, let's say non-Abelian field strength. And ultimately, here I'm doing something relatively, it's not particularly deep. I'm realizing the Yang-Mills term, introducing an auxiliary field H in this fashion. And in this expression, therefore, we have these new fields, the H, D-1, those are D-1 forms that take value in the Lie algebra of the group that we want to study. And as it's sort of apparent from its quadratic action, it's an algebraic action, and the equation of motion fixes it ultimately up to prefactors to be the D+1 dimensional Hodge dual of the field strength F. So that, for instance, it shares with F the same gauge transformation, so for instance. And why is this something that can be interesting? Essentially because if we rewrite the action in this way, then there is a way of having a strict g² equal to 0 limit at the level of the action. Because as we can see, essentially by construction, then the appearance of the H star H term is going to be, it's gone in this case, and we are left with the advertised non-Abelian BF action. And interestingly, in the process, we are changing slightly the gauge redundancies that we had in the game, because when we look at of course, the original action, we have usual gauge transformations for A and for F, as reported here. And as I mentioned, for instance, we see from the equation of motion of H and also the action in terms of H, that it transforms essentially the same way as F. But once we take the strict g² limit equal to 0, essentially there is a new gauge redundancy for H that appears. Now we are also free to shift it by the covariant derivative of some globally defined object that also takes values in the Lie algebra G. And ultimately, this gauge redundancy emerges thanks to the Bianchi identity for F and sort of integration by parts. This is sort of well-known symmetry of this non-Abelian BF theory. So the take-home message from this slide is that this reformulation allows us to take this G goes to 0 limit in this way at the level of the action in a sort of controlled fashion. And as it was indeed pointed out in the question, that's not to say that the theory is gapless in the AR, because indeed they are sort of massless gauge bosons. What is happening with this prescription at the level of the action is that we are capturing a sector of flat connections, because that's essentially what the equation of motion for H is in this non-Abelian BF theory. So the claim is that or sort of this perspective gives us a way, a conceptual path to connect the Yang-Mills theory in D+1 dimension, which is not topological and it's not a free theory if it's non-Abelian, to this topological non-Abelian BF theory with the idea that we are capturing flat connections. And even though in our paper we have stressed the case of non-Abelian symmetry, a very similar manipulation introducing again this sort of extra field H and performing very similar steps can also be done in the Abelian case. So ultimately, in a sense, I believe that this is a general story that in a sense allows for it's a systematic prescription, if you wish, to transform what we think of as the usual kinetic term for gauge fields, so either the Yang-Mills term or the Maxwell term, into this sort of topological avatar, which is this BF-like theory, potentially non-Abelian. Right, so I hope this sort of addresses also the question itself.
Yeah, so just to be sure I understand the status of the word duality that you're saying. So the claim, I think, is that Yang-Mills theory at zero coupling is equivalent to that BF theory, where however you are in the path integral, you are not modding out by the H-gauge transformations, and they behave like massless modes, which reproduce the expectation that Yang-Mills is gapless. While the BF theory is when you are also modding out the gauge transformation. And this just capture a sector of the theory. Is this correct?
Let me think. So I agree with the statement that we are capturing a sector of the theory and not the full theory, because indeed we don't see well, yes, we wouldn't be topological. In terms of the modding out or not by gauge transformation, it's an interesting point. I think I will have to think about it. I'm not sure if I have
I think that when you do this trick of introducing this H, you start from the original path integral, and since you have this term which is quadratic in H, it is not invariant under the gauge transformation. So if you integrate this in, you are performing a path integral where you are not modding out by that gauge transformations. This is something that you're allowed to do only in the infrared because the quadratic term vanishes, and then you have this sort of emergent gauge transformation. But when you want to claim a duality, the duality of Yang-Mills will be with a theory where you are not modding out by the gauge transformations.
Yes, indeed. I mean, yeah, as I was like, yeah, I agree. Like the way I think about the action in its original form before we take G Yang-Mills to zero, I don't think of H as having gauge transformations. Indeed, I think of it as something that, well, except the usual ones, but those are okay because there is a trace as usual, so we don't sort of have to worry. But indeed, at that level, I'm not thinking of H as having this sort of shift that only emerge precisely in the sort of strict G goes to zero limit at the level of the action in this fashion. So yes, I think I agree with your analysis ultimately.
Yeah, just another small comment that indeed in the case in which the bulk is two-dimensional, this H will be a scalar, and it does not acquire new gauge transformation. Indeed, it was already known that in the case of 2D, there is an exact duality because Yang-Mills is quasi-topological. So when you send the G to zero, it becomes topological. Yeah.
Yes, thank you. That's also a very good point, indeed. Okay, good. Let's see. So yes, this part we have covered. Okay, so essentially, yes, that was the sort of the conceptual bridge between Yang-Mills and the non-Abelian BF theory. And now I would like to establish another sort of conceptual connection. And essentially, I would like to show you how this, like, why would we consider this specific regime and this specific subsector I mean, the one where the Yang-Mills coupling is sort of going to zero. And actually, we'll see it's quite natural from a stringy point of view. So to get there, I would like to give you a brief reminder. Yes.
Before you proceed, can I have a quick question? So If I take your topological field theory and place it on a closed manifold with no boundary, does it have infinite partition function?
Oh, very good question. Let me think. I cannot rule it out because indeed, like we are leaving, this is somehow related also to a remark I wanted to make at the end. As you probably noticed, I'm not using a rigorous mathematical language, and I do believe that some of the properties that we're more familiar with in the context of topological field theories that govern finite symmetries have to be relaxed. So related to your question in particular, I suspect that that might be the case, but it's also, though, that also, I think, brings to the point another question, like, do we, if it's really maybe necessary or not to consider a partition function of this model on a closed t+1 dimensional case. So this sort of resonates for me to some observations also made by Fried and collaborators on how presumably in order to harness the power of the sandwich construction, we do not necessarily have to require all the usual axioms of sort of TQFTs to hold in the t+1 dimensional bulk, and rather maybe we should think of the t+1 dimensional bulk as a sort of once categorified d-dimensional field theory. So I'm not sure if I can give sort of a very sharp answer to your question, but it's an excellent point, and I do believe that some infinities will probably show up due to the sort of continuous nature of the fields involved.
Okay, thank you.
I actually have a slightly related question, which is just, yeah, will you talk later, or do you talk somewhere else about the, like just the properties of this bulk TFT itself, how many lines it has, what kind of algebraic properties it has, or is it mostly just specified by
I
this
will have
action?
some.
Okay.
No, in a sense, yeah, the action is sort of a possible way to think about it, but indeed, after this sort of part, the more stringy part, which we can also make a little brief, no problem, I will discuss some of the extended operators that we see at the level of the sort of from the action, sort of how they interact.
Okay, great, thanks.
Okay, so let's have a quick look at sort of why this is tied in with sort of string theory. And here, what I have in mind is the string theory as a tool to realize non-gravitational theories. And one way to do this is essentially to, loosely speaking, compactify on a non-compact space. So select as internal manifold a suitable non-compact singular space so that there are localized degrees of freedom supported at the singularities, but at the same time, the volume of the internal space being infinite, we don't have dynamical gravity in d dimensions. And there are many, many interesting variations on this theme, but let's focus on one in particular, which would be, for example, M theory on a Calabi-Yau threefold. So this is something that realizes a 5-dimensional QFT for us. And a particularly interesting and sort of clean case would be a Calabi-Yau, which is also a metric cone. And in that case, the base of the cone has to be a so-called Sasaki-Einstein space. So it satisfies a suitable differential geometric condition, and the resulting construction engineers for us a 5D SCFT. And what does this have to do with sort of global symmetries? The idea is that in this framework, there is a very sort of flexible way of introducing non-Abelian continuous symmetries, essentially by considering non-isolated singularities. So what we are most interested in is this sort of degrees of freedom that live at the tip of the cone, the sort of red star in this cartoon, but we can also allow for other singularities that extend, as you can see, away from the singularity and actually along the radial direction of the cone all the way to infinity. And to be a little bit more concrete, here I'm leveraging the fact that if we take M theory on a ADE singularity, something like C2 modulo an ADE discrete subgroup of SU2, we know that it engineers for us a 7-dimensional gauge theory with gauge algebra precisely labeled by the same sort of ADE data, corresponding ADE data. And therefore, loosely speaking, we are embedding our degrees of freedom that live at the tip of the cone, the, sort of the red star, inside a higher dimensional gauge theory, so that from the point of view of those degrees of freedom at the tip of the cone, we have a flavor symmetry. We have a global symmetry, a non-Abelian of this with this gauge algebra type ADE. And as I mentioned here, from this point of view, we would like to use, it's really important that the singular locus C goes all the way down to infinity and formally pierces this sort of base of the cone at infinity in this locus I'm calling sigma. And why am I emphasizing this point? Because we know from several points of view that it's very fruitful to really think about a bridge that connects the geometry of the geometric engineering construction, so the cone with its tip and then sort of the link at infinity with the sandwich picture. In a sense, there is a precise correspondence. The physical dynamical degrees of freedom that live at the tip of the cone will be mapped if we formally reduce on the link geometry to the t-hat side of the sandwiches, where we have our non-topological dynamical things, reducing sort of the 11-dimensional effective action of M theory on the link gives us the bulk theory S. And formally, we think of the link at infinity as being the symmetry boundary. This fits with from many different points of view, the choice, say, of could be like global structures that depend on asymptotic fluxes at infinity, but this has been tested to a higher level of precision recently using this idea of having branes at infinity, for instance, something that I have also worked on, and it's a way of capturing ultimately symmetry structures by doing something we might refer to as geometric engineering at infinity. So if we adopt this point of view, so let's focus on essentially what happens at the link in this sort of limit of infinite radius, and we combine this ingredient with the previous slide, we essentially get to the point I would like to make, because if we focus on the link reduction, this locus C intersecting the link on sigma will support a Yang-Mills type of action. And crucially, in this action, the gauge coupling is governed by the volume of sigma. This is what usually happens whenever we have essentially a higher dimensional brane or locus that gets wrapped onto this on a compact cycle like sigma. But the point is that the volume of sigma in the metric of the cone itself diverges as we approach infinity. So it's, in a sense, natural to think about it as a quantity that grows as we approach the region at infinity, which is the one that is relevant for the study of symmetry structures. And therefore, it gives us a motivation to why we should consider sort of the limit where the Yang-Mills coupling goes to zero. And in a sense, yes, so this is a very general story, and it can also be made more precise if we wish. Here I wanted to flash briefly a concrete example, but I'm also happy in the interest of time to skip it, no problem. It was more like to show sort of algebraic, some equations, if you wish, that realize these singular loci. There are 3 of them in this example, but we could equally consider examples where there's only 1, and but the philosophy is the same. So here there is an explicit characterization of sigma as sort of a circle inside this link, and it's very explicit that the circumference of this circle is governed by the size of the overall link, which itself scales to infinity as we move along the radial direction. So in this case, we find 3 different copies of Yang-Mills with gauge algebra SUN corresponding to 3 different factors in the flavor group. And for each of them, sort of, we have this specific limit where we freeze away, like we go to this limit of vanishing Yang-Mills constant. So in a sense, we can also rephrase these considerations as providing a derivation in the context of string theory of this point of view for continuous non-Abelian symmetries. And while supersymmetry is really important to have control over these more stringy considerations, nonetheless, the proposal is applicable to also clearly non-supersymmetric situations. Okay, so after this, yeah, maybe I'll mention briefly in words that the same sort of considerations can be done in holography, and essentially there it's a game of scaling with the holographic coordinate as we approach the conformal boundary with manipulations similar to the ones we have seen in the field theory case. We can achieve a similar result. So in this case, essentially, it's approaching the holographic boundary is what brings us to this regime where at the level of the action, we are effectively killing the Yang-Mills coupling.
Another question, which is related actually to the previous one. When you derive this proposal from either geometric engineering or holography about the Yang-Mills at zero coupling, is there something in the string theory construction which tells you that after you take the zero coupling, you also have to mod out by the H-gauge transformation, or it's something that you are putting by hand?
Let me see. I would say that I'm using the stringy considerations to essentially, well, to motivate the two main ingredients, like why having a Yang-Mills action in one dimension higher, and why consider the limit where the Yang-Mills coupling goes to zero, because that sort of gets either geometrized or sort of baked in the radial direction. It's in terms of like whether there are sort of stringy modes, non-topological stringy modes that maybe extend to infinity, so to say, that's probably a more subtle question. It requires a little more careful analysis, I would imagine. So in that sense, I'm not sure this is settled. No, it's true. It's a fair point. But indeed, I have to admit that the analysis I am presenting at the level of the action, as you can see, it sort of very closely mimics the purely field theory analysis. And there the point of view was essentially to regard H as something that does not have gauge transformations at finite G Yang-Mills, and regard its gauge transformation as emergent in the strict G squared limit. So I would essentially mimic the same sort of line of reasoning in the stringy setup, but I agree, it would be quite interesting to see whether there are independent arguments that one can make to clarify this point. It's a very good question.
Thank you.
Okay. Right, and then finally, as promised, let's see some of the extended operators in this theory and how we recover, for instance, some aspects of representation theory. So probably the easiest operators to describe, in a sense, both in the full-fledged Yang-Mills theory as well as in the non-Abelian BF avatar, are Wilson lines. Those are completely standard, labeled by a representation of our group. And in the topological theory, they are topological because on shell, we only consider flat configurations. And here, here I'm stressing the Wilson lines for A, because those are the ones that are sort of clearly defined both in the Abelian as well as in non-Abelian situation. In the Abelian situation, we can also consider Wilson surfaces for H. And they're also topological in the BF theory because on shell H is closed. But on the other hand, there is no obvious generalization to the non-Abelian situation. It would be something like a higher dimensional version of a path ordered integral, and that's not something that is well defined. It's not something we have at our disposal. But so in a sense that can be regarded as a question, that this BF theory poses. And I believe that the point of view that sort of stresses its logical connections with Yang-Mills also helps in this sense, because it shifts the focus on other operators, namely on Gukov-Witten operators. Here I'm referring to the fact that we can consider either the full Yang-Mills theory or its topological avatar, and essentially construct something that we might refer to as a vortex solution. This is sort of a solution that is defined everywhere except for some d-1 dimensional locus. I'm calling it curly C. And essentially, it's a configuration where the gauge field is the volume form on the circle that links this locus that we are removing. This is a fairly standard construction. What I'm emphasizing here is that if we think of this gauge field configuration, it is a bona fide solution to both the Yang-Mills classical equation of motion as well as to the equations of motion of the BF theory. So following ultimately the path, the philosophy of Bukov and Witten, we can imagine defining operators that are defined by performing the path integral, restricting to gauge configurations that approach this specific solution near the locus curly C. And as it's well known, these solutions are precisely such that we have a non-trivial holonomy as we go around the circle that links curly C. And crucially, the holonomy is not quite gauge invariant. It's rather only defined up to conjugation in the group. And that's why we recovered the well-known fact that Gukov-Witten operators in the bulk, both in the Yang-Mills theory as well as in the PF theory, are labeled by conjugacy classes of the group. And ultimately, what I would like to do in the next few minutes is show you how this picture gets slightly modified when we have a symmetry boundary. But in order to do that, I first have to introduce the symmetry boundary. Here, I do not claim to at all to exhaust all possible boundary conditions. I'm focusing on the one that I would like to study, the Dirichlet boundary condition, because that's the one that implements for us the zero form, the non-Abelian zero form symmetry we want to discuss. And interestingly, it's easy computation to verify that in both versions, so both in the full Yang-Mills theory as well as in its topological avatar, the Dirichlet boundary conditions do indeed make the variational problem well defined. And in the topological case, this is also a gapless boundary condition, so it sort of fits the brief of the sandwich construction, the expectations of the sandwich construction. And what we can do now that we have essentially this theory that has this Dirichlet boundary is to consider something that we might informally refer to as a half vortex. So here I'm thinking of selecting a specific d-dimensional locus. I'm still calling it curly C, but as you can see in this cartoon, it lives inside the symmetry boundary, sort of anchored there. And therefore, as we can also see from the picture, at this time is not quite linked by a small circle anymore, but rather by a semicircle or a small interval. Nonetheless, we can still write down quite explicit solutions that sort of solve the equations of motion everywhere except at the singular, at the locus curly C, as well as solving the boundary condition, the Dirichlet boundary condition that we are imposing. And crucially, when we have Dirichlet boundary conditions, we restrict our bulk gauge transformations to be such that they vanish at the boundary. And as a result, if we consider now the path ordered exponential of the connection along this semicircle, it is actually labeled by a group element as opposed to a conjugacy class, because ultimately the endpoints of this open Wilson line, if you wish, lie on top of the Dirichlet boundary, and therefore this would not really be gauge invariant if it was sort of floating in the bulk, but being anchored at the boundary is an allowed configuration. And in a sense, this resolves what might look at first like a puzzling state of affairs, because we have something of codimension 1 in the boundary that can indeed be non-Abelian, but then this something like looks like codimension 2 in the bulk. And of course, it's natural to ask, how can something codimension 2 be non-abelian? And indeed, the picture that emerges is that there is, in a sense, a stark contrast between the abelian and the non-abelian case. In the abelian case, as we have seen in the toy example of the Zn BF theory, we actually have topological operators that are labeled by group elements already at the level of the bulk. By projecting them onto the symmetry boundary, we directly obtain the object of interest, namely the abstract symmetry operators S. And as I mentioned earlier, the action can be inferred from linking in the bulk. Whereas in the non-abelian world, we see that in the bulk, we have operators that are labeled by conjugacy classes. And while on the other hand, on the boundary, sort of anchored there, we have operators labeled by group elements. In particular, this sort of simple relation by projection is no longer valid. And what is true instead, it's that projecting a bulk operator effectively produces sort of an averaged version. And while this notion can be, it's easier to make precise for finite symmetries, I believe that there should be a way of making sense of this notion also in the continuum case. And moreover, I would like to emphasize, we'll see in a moment, that now we can no longer rely on linking in the bulk. It's not straightforward to turn the linking on the bulk into action on charged objects. And also, I would like to point out that, as also has been worked out recently, these Kukov-Witten operators actually exhibit very rich and interesting non-invertible fusion rules. So it's almost as a sort of a heuristically, we could say that effectively what is the non-abelian nature of these operators when they are codimension 1 objects stuck of the boundary is somehow traded for these non-invertible fusion rules, where they are instead regarded as bulk objects labeled by conjugacy classes. So there is an interesting sort of interplay here of these different ideas. And as advertised, as a final point, I would like now to discuss some aspects on how we recover sort of some basic features of representation theory using the sandwich construction. And here, really, as probably it's not really surprising, the key ingredient is a Wilson line that we use as one of these operators that are stretched between the two sides of the sandwich. We will focus on the topological side of the story. We can be quite agnostic about the specifics of the physical boundary. And this configuration is indeed allowed if we use Dirichlet boundary conditions for A. So now the main focus is going to be on the left part of this figure. So the first observation I would like to make is that is the following. What would happen if instead we were to project a Wilson line for A parallel onto the boundary? Well, the expectation is that we should get something trivial due to the Dirichlet boundary condition for A. But a slightly more precise statement is that upon projection, we get sort of n times the identity line on the symmetry boundary, as can be seen essentially by the fact that we get the trace of the identity in the representation that we want to study. And in a similar way, we can ask ourselves what happens if we consider instead something like this L-shaped configuration. And that's an interesting notion to consider because, as we see in the picture, it gives us a sort of a canonical junction between this Wilson line that sort of hits the symmetry boundary perpendicularly and this n times identity line that emanates from it. But on the other hand, what we want to study are like endpoints. Bona fide endpoints. For simplicity here, I'm only considering untwisted sectors. And in a sense, those can be regarded as junctions between our Wilson line and one copy of the identity line. And by sort of a partial projection, we can resolve this endpoint as a junction between one copy of the identity line and n copies. And that ultimately is the same as an element in a n-dimensional complex vector space, so that we sort of recover a first feature, namely that we should really think of the endpoints as being, if you wish, the components of our multiplet. The final piece of the puzzle, so a question that emerges naturally at this stage is, but what about the matrix, the n by n matrix that represents our specific group element acting on this topological junction? And that can also be seen in this language. We can see it, for instance, again, by sort of using this L-shaped projector and projecting it on top of these S operators we had discussed earlier. So the S operator was the thing that was built on the sort of half-vortex solutions. And so this sort of projection operator gives us these sort of junctions that I'm denoting J0. And as we can see, they connect n copies of the identity line to n copies of the identity line. So we can indeed think of them as ultimately n by n complex matrices. And as it was worked out in this sort of in the various references on how the SymTFT
Hopefully he returns. Oh, okay. Well, we'll give him a few minutes to see if he returns, but yeah.
see if this works. Okay, great. So yeah, thanks. Sorry for the interruption, like technical difficulties. Indeed, so the idea of the projection gives us these junctions J naught. We can think of them as elements in a vector space of matrices, and the neutral consistency between fusing on the boundary and performing these L-shaped projections tells us that they indeed form a linear representation of the group we want to study. And indeed, the final piece of the puzzle is the realization that acting on the endpoints, or rather this S naught vector that has resolved the endpoint as a junction with the orange symmetry topological defect is the same as acting with the matrix J naught on the vector S naught. So that so in this way we can use the sandwich picture to recover these familiar features of the action of a non-Abelian continuous symmetry. Okay, and I would like to make some brief remarks engaging mostly to emphasize that there is, of course, a profound difference between gauging a discrete symmetry and gauging a continuum one. In gauging a discrete symmetry is a topological operation. It doesn't change the local dynamics and essentially would amount to a modification of boundary conditions, as I mentioned earlier, and it has been worked out in a plethora of different examples. In the continuum case, well, in principle, yes, we could maybe consider continuum groups with a discrete topology. That's a logical possibility, but it's not what is usually done when we gauge continuous symmetries. Usually we have a more traditional topology, and that therefore we introduce gauge mediators, solid and instantons, and we definitely modify the dynamics. But there was this very interesting proposal in this recent paper on how this actually translates in a systematic way onto a modification of the symmetry TFT in a very sort of controlled way, governed by ultimately something like an anomaly polynomial in two-dimension hires. And I believe that an Abelian generalization is feasible, and it's something that we're thinking of at the moment. And the final remark I would like to make on this topics is that actually, it's a general feature that we can think of 't Hooft anomalies as obstructions and obstruction to gauging. And in this language, they appear as additional couplings in the SymTFT that would obstruct Neumann boundary conditions. So essentially, we would be stuck, so to say, with the Dirichlet boundary condition, and attempt to consider alternatives would be rendered inconsistent by these additional couplings in the bulk. Good. Okay, so this brings me to my final slides. So in summary, we have seen that we can, there is a candidate theory for the bulk of the SymTFT in the continuous non-Abelian regime case. And it's this non-Abelian Yang-Mills theory considered in this zero coupling regime in the flat sector in the way I discussed at the level of the action. And in particular, this correspondence creates an interesting and I think quite fruitful connection between various points of view. So in particular, we can, on the one hand, inherit some intuition that we have from Yang-Mills theory into the realm of the non-Abelian BF theory, which might be slightly less familiar. And also, we establish a connection with stringy constructions where this regime of having a Yang-Mills theory at zero coupling emerges in a natural way. And we have seen how we can avoid some difficulties, for instance, avoiding the problem of trying to make sense of surface-ordered operators, shifting the focus on operators of Book-of-Witten type, and in particular how this point of view helps us clarify the fact that in the non-Abelian case, the symmetry generators are sort of anchored at the boundary labeled by group elements, whereas the things that can sort of exist in the bulk and are labeled by conjugacy classes. And there are many things that would be interesting to consider further. On the one hand, something that I think could be quite fruitful to sort of flesh out more explicitly the properties of the bulk theory is to recall that there is yet another way of thinking about Yang-Mills theory at zero coupling in terms of a semi-Abelian theory. This is an idea that has sort of a long and rich history and also has been applied recently in very interesting papers in the context of non-invertible symmetries. So I believe this could be an interesting direction, maybe to shed more light on this proposal as well. And I mentioned briefly 't Hooft anomalies, but clearly it would be beneficial to have a more systematic study. And as I mentioned in sort of introductory part, ultimately, of course, we're not necessarily interested in continuous non-Abelian symmetry per se. Those, of course, are a very well understood topic, but we would like to cast them in this modern language to connect them to things like higher groups and potentially also categorical symmetries. And finally, also related to a question that was asked, more mathematically, I have to admit that I do not know what the precise mathematical framework to describe these objects should be. And I do believe, though, that it's an important question. And it's definitely going to be something that can help us also flesh out more the physical implications if we have better control on sort of these models that are topological but go beyond the sort of standard framework that works for finite symmetries. And yes, and I think with that, I'd like to stop and thank you for your attention.
Hey, thanks a lot. So yeah, if people have questions, feel free to ask, but I'll open with one. So just to summarize, so pretend we're just in the simple case where you have a 2D physical theory / boundary and a 2+1D 3D bulk. So what is the content? What is the operator content of the bulk theory? Let's say for a U1 or an SU2, is it like what it has lines and surfaces that are? Or can you explain to me what the what are the lines of this 2+1D theory? Or
yeah, well, I mean, here I don't really claim to have an exhaustive list, but the ingredients I'm focusing on are the Wilson lines, which are sort of universal across dimension and across abelian and non-abelian, and then these essentially these Gukov-Witten operators.
Okay.
So they're always codimension 2 objects. They're always labeled by a conjugacy class, which sort of clearly collapses to a group element in the abelian world. So one thing that is, so in the abelian case, we have an alternative point of view as Wilson surfaces for this other field H, the sort of BF partner of A1, so to say. So that's a picture available in the abelian case, but indeed, to the best of my knowledge, it's not clear how that would work in the non-abelian situation, because it would be this sort of surface ordered generalization. So that avenue, I find it not so easy to pursue. So in this presentation, I focused on the sort of Gukov-Witten perspective, but maybe I'll take this opportunity to mention that this sort of first bullet point in the Outlook slide, in this semi-abelian theory, on the contrary, it is indeed possible to define Wilson surfaces for H. Essentially, we would have a collection of abelian H's, and then, of course, we have to take into consideration carefully the quotient by the Vibe group. So in a sense, this is one of the reasons I think this approach might be beneficial, because it gives us a more direct way to describe these Wilson surfaces for H. But essentially, in a nutshell, yes, I would say Wilson lines for A and Gukov-Witten operators. The latter can also be regarded as Wilson surfaces for H. And those are the simplest possible operators. But yes, I'm not claiming a sort of a complete list. And also, maybe I can mention, there could be couplings that depend on dimensions. Like, for instance, this is something also that has appeared in recent work. There could be, depending on the dimension, we could have a quadratic topological coupling for the BF partner of A. So here, essentially, I had something like H wedge star H. This would be something like H wedge H. That can appear depending on the dimension in some cases, and it has interesting consequences, and it modifies the operators that we have. So the things I'm describing here, in a sense, pertain to the more vanilla version of the story, and something that is universal across dimensions. But then looking at specific examples, it could be even richer.
Okay, thank you. Are there questions from other folks?
In 1+1D, we don't have to worry about the surface order integral, right? So in 1+1D series, so we need to consider 2+1D TQFTs, and all the operators are lines. So there's no surface operator. Because H is a one form, and the ordinary gauge field is also one form.
H is a one form, and yes, that's correct. Yes, very good point. Thank you. Thank you for pointing out. Indeed, yes, I was thinking of a more sort of dimension independent point of view, but that's an excellent point.
Yeah. And I have another question. So, for example, if we consider the simply connected non-abelian group, say SU2, then if you gauge the SU2, we usually don't expect there's a quantum symmetry, right? At least I don't know if there's any obvious quantum symmetry after gauging the SU2 in any dimension.
Right. No, that's a good point. It's related to this. This profound difference between sort of the gauging of in the discrete world and the continuum world.
Yes.
No, it's a good point. So it could be that an easier question that it's easier in a sense that it's easier probably to address in this topological framework of the non-abelian BF theory is what would happen if we were to say, for instance, gauge an SU2 with something like a discrete topology, which sort of also resonates with the restriction that we are in the flat sector. So yes, no, I think that's an interesting question. I'm not sure whether the notion of quantum symmetry can be sort of imported verbatim, but it seems that like something that can be addressed, and it's also it's quite interesting to consider.
Ah, I see. So do you mean that if we just gauge topologically, not gauge dynamically, then there can be a quantum symmetry? Is that what you mean?
There might be. I'm sort of building on analogy with cases I understand better, but I guess in order to be sure, a more detailed analysis is required. And so actually, yes, thanks for pointing this out. It's sort of on the to-do list, I would say, in understanding better the mechanisms of sort of gauging and anomalies. I think, yes, you raise an excellent point. It is something that we should be able to understand better with these tools.
Okay, thank you very much.
I think there was maybe one more question from Enoch.
Yeah, I have a question. So I'm probably being dumb, but then back to your duality between the Young-Mills and the non-Abelian BF theory. So I noticed that you have, at some point, you have this H field where you try to integrate it out and claim that that's the Young-Mills. But what I naively understand is that this is only possible when you have, like, say, a quadratic action with gauge fields, so your integrating out procedure is well defined. But here, since we're non-Abelian, so things are actually secretly cubic in the gauge field. So is that, like, what is missing from my understanding? Like, how can you justify this integrating out procedure?
Right. I would say that indeed the way that A1 enters the action is beyond quadratic, but nonetheless the way H enters is still algebraic and quadratic. Like, because there I'm not really thinking of, say, H as a field strength or anything of any other field or anything of that sort. So it's sort of literally a collection of real fields without any gauge transformation, and the occurrences of those in the action are the only places where it appears. It's not hidden anywhere else, so to say. So while there are indeed non-linearity beyond quadratic appearances of the gauge field, for H itself, it's still a quadratic action.
So if for concreteness, let's say we're in 4D, so we have terms like phrase H wedge F one way or the other. So H is like a two-form field. Does it play like an analogous role with like the usual like B field in like ordinary SU and Young-Mills, where that B field is like the electric background field, something like that?
So I say it again, which field? The B, like
so in like usual Young-Mills in 4D, let's say we're in PSUM rather than SUN, and there's this B field that appears in your Lagrange, right? Is this similar to the role of that B over there? Is that similar to the role of H in your construction, except that one is abelian, the other is?
let me think. I'm not sure. I don't think I see a direct analogy. Also because this H is really more like a continuous object. I don't see any sort of immediate relationship to something like a discrete B field that would appear in that case. But I guess it's still quite interesting, though. It's an interesting observation, because indeed something I would like to understand better is a question maybe related to say global forms and aspects of that sort. And in that regard, maybe it would indeed be beneficial to explore analogies and couplings of that sort. But at the level of the discussion I was presenting today, I was really thinking of H as a essentially real valued quantity that it's not quite a gauge field. Not in a continuum sense and not in a discrete sense either. Yeah.
So it's more like just a Lagrange multiplier. Okay.
Essentially, yeah. Well, yeah, it's not quite that it imposes a constraint. It's essentially a way of repackaging a quadratic action by inverting the coupling so that we can take the limit of strict zero coupling in a way that is sort of manifestly well defined at the level of the action.
Okay. Probably wrap up here. Thanks a lot for the super great talk. It was a lot of fun.